Manila Bay all the way up to Montalban, to the Sierra Madre West Slope, West Slope with Sierra Madre, but it's not shown there anymore. So that's the model area to just be able to model this part, but of course you have to consider all the boundary conditions to make it easier to define them instead of guessing what should be the boundary condition here, and so on. So there are three bodies of water, Manila Bay, Laguna Lake, and this point, and then this point where it becomes a boundary condition model. The Marikina watershed is modeled using watershed model, and the watershed geometry or delineation is given to this. It's about 168 subbasins, and then times 2 left and right overland flow plains. It's quite a considerable discretization of the watershed. The watershed computes flows at each of these, downstream of each subbasin, and all the way to this point at Santo Niño gauging station. You can also compute the Rosario Weir as well as Pasig, but in this particular hydraulic simulation, I compute the watershed flow all the way to this point, and then it will be taken over by the hydraulic model, which is quasi two-dimensional. It's actually a network of one-dimensional model using UNet. I'll show you a little bit later. So the watershed model, it's quite physically based with all these components of from rainfall, interception, infiltration, and then you get some excess rainfall, which is then can go to overland flow plain, and then overland flow plain to the channels, and then all the way to the groundwater, and then it could come out later on in the downstream. And then it's quite an efficient model. It uses this discrete kernels. So that's how it looks like. For each of these sub-basin here, you can look at very quickly the schematics of the summary of equations involved. So that's for graduate students especially. Now the schematic of the model area, I mentioned about the boundary condition or the inflow upstream, which is computed watershed model, is at the Marikina Bridge, Santo Niño Bridge actually. So that's in Santo Niño and in Marikina River. So we have, I mentioned about this boundary condition here. We have the Napindan as well as the Mangahan, and then we have the Manila Bay. So just a little bit detail on the model. The model that we are using is a one-dimensional but network of channels. So we have a channel here. We have the Mangahan channel somewhere here that connects to Manila Bay. And then we have in fact one river that inflows the San Juan River, which is quite a major inflow to the entire system. But again, I was saying, I just wanted to show you the results around this area. So if you notice, the main channel is the black part. The blue parts are what we call the floodplains. And then we model it like, it's part of the hydraulic the model actually. So the equations, this is the unit model, which is what we'll use. It's essentially models network of channels. It gives us all these interior boundary conditions, culverts, spillways, weirs, so we can easily incorporate Rosario weir, etc. So the equations again look like that, which you have a separate floodplain and then main channel equations. That's the nice thing about it. So with that, essentially then, what the input to the model, the major input of course is the rainfall. So we got this science garden rainfall, almost 6 in the afternoon. I think I was talking with one of our students, Kathy. Here? Kathy Abba? Oh, okay. Because I told her that I still didn't get the data. She gave me 3 hourly data. Finally, at around 6 last night, I was able to get the hourly data from a friend in Gaza. So given that, and that's the only rainfall data that's available on an hourly basis. Then Professor Johnson mentioned about area reduction factor, which we applied 0.6. So given that, we then put it in the watershed model. So then we run the watershed model, which is a 15-minute watershed model computation. So we should assume that it's 1 hour uniform over the 1 hour. So essentially, you started with something like 6 millimeters. I didn't put it there anymore, but it went to 49. It went to, I think, 69, and then 92 was the peak. That was around 11 to 12 in the morning. Peak rainfall intensity, 92 millimeters within that 1 hour. Quite significant. If I was doing some very rough calculation, if you have only 10 millimeters or so per hour, you'll have just right at the bank, within the bank flows. Beyond that, you can already have over bank flows in the Marikina River. So that's the, so going 50 to 90, that's quite a significant amount of rainfall. So the results of the hydraulic computation is quite not so nice. This is a graphic, table, tabular result. So you can see around stations 4 to 12 is the Provident Village, just to highlight some of those areas highly affected. You have about 12 meters of depths. It's quite almost second floor, third floor, right? But this from the Talweg, the minimum elevation of the river. So maybe the Provident Village is already about 3 or 4 meters higher. So you have like 6, 7 meters high. So virtually everything is just white. Flooded. So you have this ranges from 12 from the minimum or Talweg elevation of the river all the way to 7 in the Rosario Weir area of the Mangahan, starting out of the entrance of the Mangahan Fourway. Just to give you a time series, not the time series, but oh, by the way, I'm just showing you results at the peak flow, which happens around 12 noon. Okay? So if you look at the river profile, the water surface profile, this is the profile, all the way from I'll show you a much more better plot later on. But anyway, you have again 22 elevations of water. By the way, the datum for this Marikina river or water stages we have should be minus 10.47 meters, so that it's 0 at mean normal water. So if you see 22 here, it's really minus 10 is 12 meters from sea level, or from the mean normal water. So if you notice a big change in discharge, 5,000 around here, and then 5,300, 400, something like that. So, and then you have 1,000 that went into Pasig River, 1,500. So the remainder, which is about 3,000, went into the Mangahan floodway. That's the reason why this is a Mangahan floodway here. So similarly, if you look at the velocities, you can see velocities of 3 to 4 meters per second. That's quite a lot. That's why you see this video where you have this wave going around Marikina River with a rooftop with all people and hit the ceiling of this Kumana Bridge. It all disappeared, or I don't know how many. But that's quite 4 meters per second, I would estimate. Quite significant, Peter. I'm talking to Professor Castro. We're looking at erosive velocities of about 2.5 to 3. This is quite all the way erosive around this area. That's why you have all that mud being picked up from the river. So let's say around here, you have a little less than 2 or around, but still it can significantly erode the bed. So talking about mud coming from, of course there may be plenty of them coming from the watersheds, but significant amount has also been just picked up from the river. So that's the, okay. This is a nice plot of the same thing, the water surface profile, and then the overbank elevations. If you're looking downstream from upstream, looking downstream, this is the right-hand side, and this is the left-hand side. So, just to give you an idea, if you look at the geometry, this is a Provident Village, this is SMO, within the loop, within the Tabios. So, looking downstream, Provident Village is on the right-hand side. Looking downstream, in this part of the river, it's the left-hand side is SMO. So that's the idea. Marikina. The Marikina, the famous now SM Mall, as we'll discuss it later. So, what you'll see, if you are looking downstream on the right-hand side, around this area is the Provident Village. This is a loop actually, right? It was a river bend that goes like this. So, the river banks there is about, if you look, 17 meters. The river went all the way to 20 something. Now, if you had a wall, actually this was considered the wall that there was a wall, but this part no wall, then everything just gets inside the village, right? And no way to. And what happened? I think there was a break. I mean, a wall break, right? A levee break, so to speak. That's when you know, like rushing, competing water getting into the village. On this side, if you look at the SM Mall elevations, it's about that much. And look, you have like, what's that, 15? No, 17 again to about 20. You have 5 meters. That's why the whole grocery at the bottom and the parking lot, where I think, did you show these pictures?
Yeah, 5 meters.
Yeah, 5 meters high. So that's the computation that we have in the atomic model. And then, of course, Rosario here, we have this point, this point. That's the elevation at the Mangahan is about this much. I don't know how accurate this is now. But anyway, that's just, it looks very small here. And then I mentioned about this, a little bit upstream of this, there is this, I'm not so sure if this is the right owner of that one. I'll show you. I think it's Ortiga's development. There is a constriction there. And you'll notice, although it's not quite a significant looking jump there, but that, because of the constriction, you see this elevation went up about 1 meter maybe. Maybe it's not significant, but if you are living in a house like mine, we have this one, and then about 6 more inches, it went into the bedroom and then it stopped. So that 6 inches can be quite significant if you have all your things there. Right? So 1 meter may not be so big. Actually, it's a bit over 1 meter, but that's the hump. The jump, so to speak. So that's a nice telling effect of that constriction. That's Manalo Beach, actually. That's before Manalo Beach. Downstream Manalo. I'll show you the picture later on, some issues. And we tried to do a manual based on the results on the topo map and then the Google map superposed together. Odyssey Herrera, my graduate students not here, did this last night and sent it to me at 5 in the morning this morning. He tried his best to do a low-tech, GIS kind of thing of processing of the elevation data. But notice, all Cainta is flooded. All Provident Village is flooded. All SME in the simulation model. And I think you can verify that maybe in the pictures you can show that, What I'm trying to illustrate is really, with the models that we have, even in the last 3-4 days we just did all of this, although the geometry and so on we have from other projects. If you have run simulation scenarios, this and that, you could already have determined what are the flood extent. Professor Castro in 1988 did the LHRC study, already showed this one. Maybe you have a little bit of did the flood inundation study. But how well supposedly the academe could really communicate and translate this into real world implemented projects. That's a difference. Because I remember a friend of mine was telling me that the Provident Village, Professor Castro simulation, this was all Palagi here. No Provident Village, only along that Marikina Road. But now, of course, it's a different story. You see all these houses. So that's the idea. So anyway, just some issues I want to bring up. Talking about the Provident Village, so we are talking about the SM Mall. Actually, I thought Professor Leonson showed a river park picture or a plan of the Marikina city. You did not show that, right? But I thought you gave me the slide, but I couldn't find it anymore. Anyway, there was a Marikina river plan, supposedly around this area. They showed SM Mall just a dot here. So it's like a very nice, drawing of trees and so on, nice park. And then Provident Village was not in that picture. Not identified.
The river plan is identified the Provident Village.
In other words, just for the PR or bogey points for the city, it's as if like you have a nice floodway for the river system. So anyway, I just mentioned, you just bring up a point. Is that a river obstruction? You have the main channel, floodplains. Supposedly these are really floodplains because you have a meandering river, and I talk about as a typical fluvial geomorphology guideline in design of natural rivers. You should allow for a meander belt of 6 times the river width. So if you look at this one, this is the river width. You should allow about 6 times as big as that, as wide as that. But even for this case, maybe it's not really natural sort of meander belt that you have to look into because of the developments that you already physically constrained or restricted the river. So that's not even apply. So just, I think my next slide just shows you that this is like the nature of meandering river. You have to allow for what you call this meandering belt. Don't build around that area. It's the bottom. So otherwise, you always have.
The picture with the Provident.
It's within like a loop like this, and this SM that's Providence. Very much. In other words, you should not allow that.
Allow the Provident.
What I've known is that in 75, they said there was a lady, I don't know, the city engineer or in Marikina. He did not want to give permit. But then, I don't know, maybe some of you know about this. I talked to a friend of mine, and he said that it's verified. But then she was replaced. And then after that, there was a permit. And then that's when they built. There was a building there. So, you know, the issue there is, of course, land use, urbanization, urban, and so on. The other issue I mentioned about is that construction in the Marikina River. If you look at this plot, this is the Manalo Bridge that Bong mentioned. And then there is this Rosario Weir, which is the entrance to Mandan Floodway. Now, there is this big piece of land here. This is a Google map when, I don't know what's the elevation, but you can see the sandbars or some kampong. Is it kampong? Yeah. There's sandbars here. And anyway, this was already, of course, inundated during the flood. But this part, I mentioned, I didn't say anything actually. Is it the river accretion? This one, yes, that river constriction, the question is that they were claiming, this owners, because we were in 2006 in the Andrews project, we went there, take pictures, and even a week ago we went there, take pictures, the security guard comes in, we gotta take pictures. They said, what's this? You know, we are in a public place, standing in the bridge, you gotta take pictures. You gotta take pictures because we are saying that, I think, it's not quite a river accretion, natural river accretion, but rather a reclamation. Why? Because they will expand their property and they are planning to put up a condominium shopping center. Somewhere is the Libis. Just a little bit some here. So when I say river, natural river accretion, is that sometimes rivers, when supposedly it makes a bend, maybe you have some accumulation of sediments on the side. So then, in the long term, if you You can get around, you can then claim, start with a tax, land tax and so on, and eventually maybe it becomes your land and it becomes title. Just like I think SM owns some land in the Laguna Lake between 10.5 to about 11.5 meters elevation. I suppose with LOD says that anything 12.5 or higher, it's a disposable alien, but otherwise you cannot. But of course, this one is another story. And if you think about it, I don't know how much is the cost of this Rosario here. It's rendered a little bit handicapped because of that constriction here. So that's an issue there. And then I mentioned about the Mangan floodway. So this is now the lake, Laguna Lake. This is the Rosario Weir, which looks like this. During low flow months, you have all this harassing. What I'd like to show you actually was that this is the main road, and this is the main road on the side. Supposedly, the Mangan Fly was designed to be 260 meters wide. But because of settlements, not outside, but inside the floodway, of course, they are gone now, I think, right? They just disappeared after 12 o'clock Saturday. Because they're all, just had a smooth ride to the bay, to Laguna de Bay. But anyway, so this is again a constriction. Of course, whether that's really contributed, if you have 3,000 going into the floodway, maybe you could have evacuated much more water, right? Without those what you call roughness elements, the informal settlers inside. So now that's cleaned up. So that's. So I think in conclusion, I just want to mention that of course studies have been available since the 80s on the flood hydraulics. So, and especially the advances in modeling and computing technologies. Faster computers. Maybe when Peter was doing this, you were still using IBM PC already, but maybe
hard disk was a
day. But now
hard disk was a novelty.
Okay. Because I can do it in my computer, which is 2.4 gigabytes. I did the simulations for that so many hours. For just 1 minute, the watershed model is done. Another 30 seconds, the hydraulic model is done. So the point is that with the very fast computers and with some advances in modeling technologies, you could have really used something like this for rainfall. I didn't mention about rainfall. I didn't do rainfall, but you could have a rainfall prediction on top of that, a flood forecast. Input it in your hydraulic model to make forecasts or predictions for real-time early warning systems. And of course, EFCOS was trying to do that, but of course it's BF, my BF, remove the EFCOS. That is like, I don't know, maybe we can discuss a bit later. And of course, the same technologies could also be used for long-term studies. Flood disaster preparedness plans, like for example, do some simulations and then for different scenarios, maybe then you have, you can put some rainfall threshold. That's very useful. I've seen it in Malaysia, Indonesia. If the rain has been accumulating this much, maybe you should evacuate to a different ground and so on. And I think we haven't had a flood inundation study in the Marikina River and to really show those flood lines, where people can see, well, wait a minute, the rain has been going this fast. Maybe we should already move to higher ground, something like that. And how fast it can move, something like that. About 20 years ago, we had a project. I was still a graduate student with the U.S. Army. And our project was basically to determine if we are like 2 kilometers from a river with this slope and so on, and the water is rising this fast, how many minutes or how many hours do you have to evacuate on a certain elevation? That kind of project. That was IBM XT then. But anyway, that's the idea. Of course, we can always have long-term studies, not only for preparedness, but mitigation as far as disaster management is concerned, for proper urban and land use planning to reduce this flood hazard. And then, of course, we should seriously consider or take a look at these flood issues with regard to urbanization. I think you can see a lot of these blogs or Facebook or all over the internet now, talking about how bad we are in urbanization, how bad we are in modification of waterways without really considering seriously what are the impacts to flooding. Local drainage is another one. Like my subdivision there got flooded because the drainage was removed. Good that the wall on the other side that went to another subdivision broke because the pool, the water level already leveled to the point, it went about 5 meters, maybe 3 meters in the wall. Unfortunately, people on the other side, there was a house. Everything has this debris and so on inside. Maybe they got flooded few minutes, this high, and then one of the matulong is unconscious. I think she died with it. But anyway, that's in other words, local drainage is the problem here. Although there's a local drainage issue, but it has to go beyond local. You have to look at the entire system. Of course, you have also this what we call natural versus engineered river works. Maybe there is a limit to engineering. A lot of engineers nowadays really do a lot of non-engineering measures. Like I always advocate non-engineering measures because it has to have, you have to compromise between cost, risk, as well as, is it a real solution? So you have to consider, like for example, that maybe Provident Village or even the SMO should not have been there. Now that's maybe totally. And of course, with extreme events expected due to the nice topic nowadays, climate change, I think we have to really try to do all these published studies and so on, incorporating climate change. I think that's it. That's it. As far as thank you.